and I will tell him that this is not a good behavior, but I will tell him this in private, okay?
No.
So,
I want to.
I have a sad news, that is Jakob Rehhoff.
Thank you very much.
Maybe as a present next time you get a watch that will be in time.
The watch doesn't work right now.
So, well, the sad news is Jakob Rehhoff could not come because he has a problem, a health problem in his family. And then we decided that I should make how we call it, an interlude on a topic, on two combined topics. One is I want to say something about Sharam's talk on Monday. And the second is that in July 10, there is the 100th anniversary of Karl Adam Petri, and I have recently given a small note on this, and I combined now the two things, and they're combined beautifully, as you will see, and that is what we will do now. Okay? Everybody agrees? Nobody disappears? Okay. So, if you don't mind, I'll sit down. That is better for my knees.
Wollen wir den Stuhl vorne machen?
Nee, ich kann das dann. Okay, as you see, the title is The Digital Bird. And I've chosen this title for many reasons. One reason is that Sharam has chosen the title The Computing Continuum. And I relate those two things, the computing continuum and the digital world. And you will see what the difference is. So what does Sharam do? He focuses on implementation. And here are all the catchwords of Sharam: Internet of Things, fog computing, cloud computing, holistic system, ecosystem, etc. So he's always in his mind one topic. There are some people that have already in his mind one topic. Don't smile so much. His topic is implementation. He wants to run a system.
Because he wants to get rich.
Because he wants to get rich, yeah. And I always wanted to get rich and I never succeeded. Yeah. So the main problem is, however, for which world does he want to do this? So just to have computing running up and down, a computing continuum, and it runs somewhere and nobody's interested in, makes no sense. Of course, you do it, and I'm sure Sharam also does it for some purpose, for some personal purpose. And he has in his whole list also two points where he mentions at least a little bit this, and that is he wants a holistic ecosystem. Holistic then means not only the computational stuff, but also the human stuff. And he's in the very end of his list, he also says human in the loop. Of course, human in the loop. If there is nobody wanting the things, why should you do it? So human in the loop is a triviality. And this is what Peter and I, we insist on. So not just data, but also including humans, organizations, technical devices, items. Sharam would say, well, I do it also, but only he does it a little bit. And I think this should be the starting point. We have a world in which we are people, in which we live, and sometimes we use computers, and sometimes we don't, and these are the maybe more beautiful parts of the world where we don't use computers. But this is integrated, and what we need is a decent modeling of the digital world. And digital world means a world where we live in, where digital devices play a role, an important role, but are not the entire thing. But nevertheless, we need a theory that goes smoothly beyond people and organizations and matter and computation. And such a modeling technique is not available yet, or starts to be available now. And to start this topic, I go to history. So in my age, you usually start with history, okay? Younger people don't, but I do. So what is the history of modeling in science? So since Descartes, we know dynamics is modeled in a Cartesian diagram. That is what you usually see. There is an x-axis, that is the time, and time is usually in real numbers. And there's a y-axis where you have something, pressure or speed or acceleration or whatever you density of something. So all modeling in science has been, since Descartes until the 1950s, in this framework. All technology is done in this framework. And I can tell a story about
May I challenge this? Isn't it differential equations? May I challenge you and ask whether this is true because differential equations is the model. This is only graphical representation.
I agree with you. So sometimes
unusual.
Sometimes I agree with Frank, and I will come to this not very deeply, but I fully agree with you. But then in the 1950s, we came up with this, not we here, but informatics came up with the idea to make discrete models. And this is a fundamental shift from these continuous models where we have continuous function, differentiation, differential equations. Suddenly we make these these steps. And this was done very quickly and not very deeply thought, I think. So what came up is automata. I've been a teacher for automata theory for so long, it's boring. It's a centralized view is the normal case. That time, a computer was millions expensive and tons of weight. You had one computer and you were very proud. You never had more than one. And this world, this Shah world, let me say it this way, it jumped from state to state. So the sequence of global states was the normal view on this world. The single behavior is a sequence of states and steps structured by time. That was the view. Sometimes you mentioned only the states, sometimes you mentioned only the steps, and sometimes you mentioned both. But the single behavior is a sequence of this seems to be so normal, and especially our bad education in computer science, we always do it this way. And we have, computer scientists have big problems to deviate from this and to think it may be a little bit different. And I've learned from Peter that in economy, they are more liberal. They understand much better what a single behavior is. I will tell you what a single behavior is, because so far you don't know. Okay. A single behavior is structured in time, and Sharam says we need a representation of locality, composition, and hierarchy. That's what you said, Sharam. I want to see Sharam. Sharam, a little bit to the right, that I can see your face.
Yes.
I won't always see your face.
You want to see my face?
Just to make sure what you are thinking about.
No, I'm thinking you are right from your perspective.
Okay. On Monday you said what we need is a representation of locality, composition, causality, and hierarchy.
And causality was very important.
Then I come to these three things I perfectly agree. And then you even said, and I love this even more, built-in causality is a first-class citizen of a system. I love you.
Oh!
Because this is absolutely the case.
Yeah.
And the point is, you didn't say so explicitly, but I think we all agree, I want to see your face, you can't observe causality. The question is, however, can you represent causality?
The question is?
Can you represent causality? You cannot observe it, and I will come into details of observation and why you cannot observe it. But the question is, can you represent it? And the point will be, from Peter and mine, this morning, this afternoon, you can represent it, and you must represent it to understand the system.
Because it's logic?
Oh,
You need logic.
Let's see.
Okay.
Let's see. I fear to say temporal logic, then I would hate you.
Okay.
Then I would hate you. Okay. So the digital world, this is what we have in mind. And what is the scientific basis of the digital world? This is the question I would like to put and to discuss with all of you. Okay? So the first idea would be, we want to model something. There are these fancy modeling techniques like UML, BPMN, and you know it better than me. And to model the digital world, we just take something like this. So yet another syntax, yet another semantics, the 1001st modeling, blah, blah, blah. And this is then pretends to represent the digital world. I think we all agree this doesn't look very promising. So don't do this. This is not the right way to do, despite the fact that all informatics loves to do the syntax and then the semantics. And, but it is nonsense, it's absolute nonsense. So Ludwig Wittgenstein, because we have so many people from Austria here, then you must quote Wittgenstein. The limits of my language mean the limits of my world. So of course we need a language, we need a kind of representation, but we don't need a stupid syntax on which you put the semantics. And we should learn from other sciences, and from which science can we learn most? We can learn most from physics. And in physics, and now come back to you, Frank, in physics they have what in English is called the calculus. In German it's just called differential equations, as if it was one of many formalisms. But in English it's called the calculus, and there's very good reasons why it's called the calculus. Because this is an outstanding formalism for formulating, as I have shown you, all the continuous models that are present so far. So what do we need? We need
May I add only a single point that may be of interest to you? It's called the calculus because in the meantime mathematicians have proven that there's only a single kind of doing calculus except in 5 dimensions. In all other dimensions it's the calculus, only in 5 dimensions is the difference.
Why don't you like 5 dimensions?
Nature is this way that in 5 dimensions you have up to 7 different ways of doing calculi. In all other dimensions it's one way. Very deep theory in.
Now I have learned something.
Huh? Thank you very much. This was my intent. I learned so much from you.
Okay. So what we need is a corresponding language formalism for discrete models, for discrete dynamics. So that's what we need. A universal language for the digital world. That's what we need. And of course, one point is the relationship between the model and the modeled must be as tight as possible. And for some years ago, I've read a book on this topic where they said it's amazing how well the calculus fits the physical world. It's really astonishing how tight it is. Okay, now we must have something similar for discrete steps. We should not be so modest. We should be demanding and say that's what we need. So let's look what we have so far. What do we have so far? Computability theory. This is boring. This is just for symbol crunching automata. That is verified. There's nothing wrong with the computability theory, but it tells you all the stories about numbers, maybe numbers, and symbol manipulation. And the digital world is not about symbol manipulation. I think that is what we have seen so far, and also what Sharam has, I think, in his mind. So we need something else. What we have so far is a general collection of technicalities So UML has 1,000 pages. This is not a basis for anything. It's just 1,000 pages of blah, blah, blah. Okay. So let's start thinking about such a universal language for digital world. How do we do this? Well, our first observation is we are in Greece. And if we are in Greece, we start with a philosopher, of course. And so we look what is going on since the times of Aristotle. And he invented, and this is used since his times, the notion of a proposition and the notion of a predicate. Proposition holds or doesn't hold. Okay? So the sun sends light, this is a proposition, and in our world, at least the world we are interested in, it holds. Another proposition, another predicate is, predicate does apply to an item or does not apply. Okay? For instance, to be a leap year. 2026 is no leap year. 2028 will be a leap year. And this is true forever. And now comes one, only one, but the most excellent, the most important idea. So everybody who was sleeping so far should wake up. But nobody was sleeping so far as I can see. Only some were looking to their laptop instead of listening. It makes me nervous. But okay, now comes the big point, and this big point is not from me. It is from Karl Adam Petri, and it is the fundamental idea of Petrinets. It is the grain from which everything else follows if you do it carefully in Petrinets. And the idea is extend logic from statics to dynamics. Okay? Now some people agree. I'm surprised. I'm happy. So a proposition sometimes holds and sometimes doesn't. For instance, the restaurant is open. Sometimes it holds, sometimes it doesn't. And as a predicate sometimes applies and sometimes it doesn't apply. For example, if you have many tables in the restaurant, then table number 2 is free, and table number 4 is not free because it's occupied by somebody who is eating. And this kind of making logic dynamic. This is the fundamental idea of Petri. And the question is how to do it in a really decent way. Because if you don't be very careful to start to say, oh, it's a good idea, and after 2 steps you are doing this automata theory again. And this is not what should be done. It should be really taken very, very serious. Okay, but I think so. The next step is clear. Predicates can be updated using events. And this is the new word, an event. So the update of a predicate is called an event. An update of a predicate means the predicate does not hold, in this case, the table is not taken in the moment, and after an event the table is taken.
Then you don't mean the predicate, but the values that are used in the predicate. The predicate is a string of symbols, and if you have the t as a parameter, and the t parameter changes, then the table is once free, the table is not free. So there's a difference between a model and the instance of the model. Go ahead.
We are doing logic.
Yeah.
In logic you have a...
But even in temporal logic, if you want to
mention temporal logic. It is so stupid.
to me, as of now, you describe temporal logic. Okay, I think
Absolutely. I tell you what temporal logic does in terms of logic.
Yeah.
So serious predicate logic applies to structures.
Yes.
A structure is a finite collection of sets and functions.
Yeah.
So, temporal logic assumes a special kind of structure,
Absolutely.
namely a transition system,
Yes.
where you have nodes and arcs. You have something like, yeah. So this is already not a nice logic because it applies only to very special model, to very special structure.
But the examples you gave are very fine in temporal logic. The table is not free, in the next moment it is occupied.
You can, so far you can model it in several
Thank you very much.
here. But you don't make me happy when you mention this, because later on we come
A
to...
friend of mine always says your happiness is optional. Go ahead.
Okay. Okay, so I make it a little bit more clear. You have a set that is the set of tables of restaurant, and you have the predicate that it is free, the table is free, and in this abstract sense, predicate is just a subset of a bigger set. Okay? The subset of to which this applies. And now we make, like in mathematics, you must represent it somehow and to represent it as a circle. Okay? This is not a syntax. Don't think I start building a syntax. It's just in mathematics you have the integral symbol and the plus symbol. You could change it by something else, because the idea is not the symbols, but what is behind it. And in this sense, we want to speak about predicates, and we just make a picture, and this is a circle. And if an element applies to this, then you write the element inside the circle. And now this means the predicate is free, applies to the table number 1. It may also apply to other tables, but at the moment I'm only interested in table number 1. Okay? Nothing else. And now I want to represent an event. That is, the table is no longer free, but somebody is apparently sitting down the table, and we draw it this way. Okay? This just tells you the table number 1 is free, and now somebody, a client sits down, and then the number 1 disappears, and the table is no longer free. Everybody understands? Small break for me. Okay, this is just a graphical representation, and predicates and their updates, these are the seed of a theory of discretely involving systems. Okay? This is a decent foundation of something, because logic is undisputed and basic of everything in science, everything in mathematics. And this is a wonderful basis for the theory of discretely involving systems. Okay? And not UML. Okay, now maybe there is a set of clients of the restaurant, and the client is waiting for dinner. So he's waiting, and there is the predicate, and Alice is waiting to be seated. And also she will be seated if the same event occurs. Now we have the same event, and to make it clear that it is the same event, we draw it like this. Okay? So now we have two predicates, the is free predicate and the is waiting predicate, and if this event occurs, both is free applying to table 1, is no longer applying to table 1, and is waiting applying to Alice is no longer applying to Alice. And now there may be the case that Alice is ready to order food, and then we draw it like this. So this means if this event occurs, then Alice is ready to order food, and also this is the same event, and then we draw it like this. Okay? And some people of you, I see, they are smiling and thinking, doesn't it look like a patronymic?
No,
And
it's very...
I promise you, it is not by chance that it looks like a Okay. Now, there may be the case, now better is a bit quicker. If Alice is sitting on table 1, is ready to order something, then it may, after an event, be the case that she purchases fish, and this glues in this way, and then we can glue many of these things together. Okay, now you have, first time in your life, you have understood what a patronage is. So far, we were told a patronage is a triple, something called bases, transition arcs, etc. Like a syntactical formalism, and then we gave it a more or less beautiful. No, this is not the right way. The right way is the patronage is a predicate transformer, so to speak. A this is only symbolic representation. Okay? That is really scaled to big systems. And now I show you something that you cannot read because it's written so small, so don't even try to read this. This is the first event in our history we've seen already. Can you read this?
Yeah.
Ah, you can read this?
Absolutely.
I cannot read this. Okay, so because this step we call A. And we write it as an algebraic expression. We just write A. And now I go quickly, there's a B. And now we write A composed with B. Okay? And then there comes a C. So the C means Alice takes the menu card. The menu card, and she orders something, and then she's waiting, and her order is given here, and the menu card is free again. Come back to the menu card later on, and then the fish and the chips are cooked concurrently, and then served, and then she eats, and then she pays, and then she goes. Okay, so this is one behavior. Of course, now you say, yes, I see. It is a sequence of steps, It's almost. Here we have two in parallel, but this is not very exciting. We still have a sequence. Don't laugh too early. Because now I have a second client, that is Bob, and he also takes the menu card. It is a little bit strange restaurant, it has only one menu card in the whole restaurant, okay? I agree, this is not the standard way of processing menu cards, but in this restaurant, you have only one menu card. So Bob sits down in a completely, in his own local world, he sits down, he takes the menu card, orders something, then he gets his meals prepared, and then he eats, and etc. And now we want to come, and then we write, Bob, maybe I should go back. For instance, Alice, we can write in algebraic expression A composed with B, composed with C, etc. Just write it like this way. And this is extremely important because Sharam wanted abstraction. Here you have abstraction. For the whole process, you only write Alice. Okay? If you like the Bible, so for the whole Bible, if you don't want to read the whole Bible, just call it Bible. Okay. So this run, we just call it Alice, and if somebody wants to know what it is, he goes to the algebraic expression. If he is not interested in details, call it Alice, and that's enough. So we go to an algebraic representation, and again, algebra is a mathematically well-established thing. So I only use well-established mathematics, nothing else. And as I said, here we have Bob, and also Bob can be written in such a way. And now comes an important point, to compose Alice with Bob. And the only thing where they compose is, first Alice takes the menu card, and then Bob takes the menu card. But initially Alice and Bob start completely detached. They have nothing to do with each other. And also after they have ordered their menu, they sit in different parts of the restaurant and have nothing together. And this shows you causality. So causality means there is an arrow, so to speak. Causality means first you order, and then you get your meal. So whenever you have a sequence of arrows, that is a causal dependency. Causally before, causally after. But Alice and Bob have almost nothing, no joint arrow sequences. So whenever Alice is eating the stuff, it's causally completely independent of the stuff of Bob. And here you see this is a representation of causality. And what is most important, or likewise important as causality, is causal independence, the complement of causality. Two things have nothing to do with each other. And to understand the system, if you can identify things that have nothing to do with each other, this is where you start understanding the system. Of course, you also want to know what is dependent from what. But then say the rest is not dependent of anything. And here we see it is in this case, in this single run, but first has Alice used the menu card, then Bob has used the menu card, and then the menu card is there. So it is true, first, the fact that Alice has sit down and taken the menu card is before what Bob is doing. So there is a causal dependency on long sequences, but to be independent is most important. And now we have this big run, and to write it down algebraically is extremely simple. You write down Alice composed with Bob. That's all. And that represents this thing. And now I'll go a little bit quicker. This I have done on single runs. So this single run means what we have in informatics. In formal languages, it would be a single word. But this word idea is so wrong, so stupid. So here we have a very detailed representation of a single behavior, and it shows you the causality. That's what Sharam wanted to have. So this one sort of Sharam's wish list, it is clear how causality is represented. And again, you cannot observe it. You cannot observe that cooking the fish of Alice is independent from the fish, from the meat of Bob.
After the fact, you can observe it. You can follow the traces.
What is the trace?
After the fact.
The run.
Pardon?
The run.
Yeah.
Yeah.
So the run, if you
Of
observe.
course, I know what you mean by trace, but this is such a stupidity that I say I don't. A trace. What is a trace?
No, what you said you can't observe. Yes, you can observe it, at least after the fact. You can find out what happened.
And then you get this picture.
In this particular case, yes. Otherwise, if some paths are not taken, right, you can find out after the fact what happened in the past to reason about it.
So they go out of the restaurant and then in accident they meet, oh, have you also been to the restaurant?
Yeah.
Something like this.
Yeah.
And this
You
can
observe.
again. Yeah. So a trace is a sequence of something. And
Can be parallel, yeah, okay.
okay. But if it is parallel, it's different thing. But many traces are a sequence, and some of the order is justified by causality. And
No, seriously, in real-world systems, you have so many programs running in parallel. If you take a look at the traces, you see the parallelism, of course.
I think yes. No, you are with me on this level.
Yeah.
Okay. So Frank is with me on this level.
Yeah, but you just don't want to observe it, and after the end just find out why things have crashed, or why an empty table have not been seated, or why two people have seated on the same full table. You want to control it and run it, right? Like at the very end, ending up with a system. So you need to somehow transform this into something that makes it not only traceable or explainable afterwards, but putting the non-observable in something that is somehow controllable. So looking at 78 Lambert paper, putting something like a causal relationship and mapping this to something the processes can really execute.
I should not say it is not observable.
It is not observable.
It is not observable in the moment it happens. In the moment there are two events, A and then B. You are never sure in the moment it happens if A is causing B. That means B could not occur without A, or if A and B are independent.
Well, the future will tell, and
Yes.
then and
Yeah,
therefore
yes.
Frank is saying after it happened,
Yes.
you can take a look at it by some means and maybe figure out.
Have to object. You can, but the point is to transform it to something where you can ensure that causality is then realized. So in your digital world, you can build a system where at least the causal relation is maintained and communicated in the system.
I take
And
it
based
up.
on that theory, you can actually do it. Otherwise, you're kind of lost.
I completely agree with you. And you are in control of the system you build, you know causality. Yes. But if I go, okay, I take this general formulation, you cannot observe causality. I take it back. I'm sorry I have said this. I have
No, you're right, but then the point is to transform it into a system where you implement mechanisms to observe the causality or the causality that is then ensured by the consistency concept and the whole box underlying of the whole thing.
I was
Being
thinking-
aware that on a physical world, intermixed with the digital world, this will never happen. This is what physics tells. And then you are on the safe ground for theory and for formalism.
I
Be careful with
implicitly,
your words.
I implicitly thought about process mining,
Absolutely.
that they are sitting, looking at these sequences and trying to find causality, which
No.
they don't find.
You have events together with a time interval when the event took place, and then you can detect parallel.
Well, even if you don't have time, you can do causal time. This is what Lambert tells us. And if you look at
Yes.
CLA plus, it's kind of a simple thing. You have things happening in program order, so obviously A happens before B. A receive event happened after a send event.
But to mention before and after, what does before and after mean? Right.
Causally before and after. Okay, I formulate, next time I formulate it, it'll be more careful.
We should invite
You are
Lambert.
friends. You are friends.
Who?
Yeah, listen.
Lampard. Huh?
Huh?
He wants to invite Lampard.
Oh, good.
And when Lampard has written a new book this year
Yeah, about the science of
about TLA, which is, okay, TLA, and I have to make a report on this book. I'm still struggling with this report.
Oh, use ChatGPT.
So far we have spoken
Use
about,
AI.
Yeah.
no. So far we have spoken about single runs, single behaviors. And the question is, can we also do it on the level of systems? So what is a system? A system is a finite representation. I only have 5 minutes.
No.
A system is a finite representation of many runs, many behaviors, many times even infinitely many behaviors. Okay, so can we do it on also on the level of systems? And we can do this, and now I'm almost finished anyway. So this is a model of the restaurant. Here is the entry. Here is, I cannot read this, the dining room, and this is the kitchen. Okay, this is now at the system level, and you can do the whole the story again. The entry is just a composition of two events, and the dining room is a composition of 4 events, and the kitchen is a composition of 3 events. And when you want to define the restaurant, you just compose the names of the 3 things. So this represents the system. Okay? So the importance of this algebraic representation is extremely useful for abstraction and refinement. Okay, finishing. What has been gained? An epistemologically based representation of real-world items and data. And here I distinguish items and data because when you want to analyze the world, then data behave differently from items of the world. For instance, you can easily erase data, erase it away, it doesn't cost anything. But if you have a Mercedes car, you cannot erase it. You can also not double it. It is easy to double data, but it's not so easy to double it.
Classical data, quantum data can't be copied. Right?
Okay, next time I have classical.
Very
This
classical.
may be a very interesting point to discuss.
Yeah.
Yeah? Okay, so classical data can be erased, wasted away, or doubled without any cost, but items cannot. And this difference can be used to make much better invariance. Because you always know my car is somewhere. Maybe it's stolen and in one of the countries close to Berlin, where I frequently go. But the car still exists. You assume the car still exists. But if your data is gone, you don't assume that somebody has stolen them, because if you would steal them, you would copy them. So data behave differently from items. And this must be exploited in representation and in analysis. Therefore, the items must be part of the model and not only be represented somehow by data. Okay, I said invariance of real world differ from the invariance of data. We have got a universal composition operator, and we will talk about this in the afternoon. So we have modules and we can compose them. It makes not always sense to compose two completely different modules, but how to compose is clear how it works. I did not tell you all the details of this. We will talk a little bit about this in the afternoon. Refined abstraction, correctness we will speak about in the afternoon, where we have seen already refined abstraction is almost for free because we have this algebraic representation. And this is the formal basis for Sharam's computation continuum. And if you want to see details of this, come in the afternoon. And after that, read this book and let me know. Thank you very much. Maybe there's a question, yeah?
How does this relate to TLA when it comes to the expressiveness of modeling systems? Are you aiming at modeling a larger set, a subset, or pretty much the same things? And can you do some kind of transformation between the two things?
TLA is the classical world of sequences of states and steps. It has one good idea, and it is most suitable assignment statement. X gets x plus 1 plus 1 is replaced by two variables, x and x prime. And when you have the assignment statement x gets x plus 1, you can write x prime equals x plus 1. And then you can even write x prime minus 1 equals x. That is a very good idea to get rid of the assignment statement. And Lampard did it very well. But he stays in the old function. He stays in his computation work. He pretends that it is about modeling. But it is about modeling of algorithms and functions operating systems. Whereas we insist if we want to model behavior in the real world.
But if you're thinking about representing the things in the real world as something like an agent, then you transfer it into the Lambert world, and as such it behaves. Does some actions, these actions happen within a sequence, so you have the steps again? So wouldn't that be a kind of a canonical or natural mapping from this one world into the Lambert description?
No, because the real world sometimes is in the way you say, sometimes it's not. Then you squeeze it into this concept of TLA, and you have a lot of rubbish in between, and you have to put in things that you don't like, and you must raise away important aspects. Causalities in TLA, you have no causality. No.
This is pretty much 90% of Lambert's contribution to science.
Coffee break. No, your discussion to
The discussion
But now you know.
paused. The
But
coffee
you know.
break.
Other question.
But now you know how the report will be written.
Other question, please.
In the beginning, I naturally felt the urge to defend ourselves, let's say, but after noticing you actually want to help us, that's very much appreciated. What I noted in this model is like the first thing, where is temporality, first of all, and the other thing is where is stochasticity in this sense. Because, for example, in this case, you would have a model where, for example, the waiter must bring a dish, but you must dispatch things at some point. So you have entities waiting. Also, Alice might not always order the same dish, but according to this, you might need different paths. So it's two things I was very much missing.
Temporality, we quote Einstein, who said, time is what my wristwatch shows. So there is no notion of time in the world. There are clocks in the world. There are clocks. And there is not a, you cannot say, now it's, I take for free and in precision square root 2. At the minute square root 2, I do something. This naive notion of time that we use.
In general relativity, Wolfgang, there is, because it's a single dimension in addition to space.
I mean,
This is also correct.
I might have to start from Einstein back then, but like it's just when I'm thinking of a system, you might need to dispatch resources, etc. Proactively. That's things when you need some sense of proactive temporality, for example.
I make it shorter. This is the fundamental 5 notions that you need. On top of this, you can start to tell me what the watch is. I didn't talk about time on purpose. You don't need, for these fundamentals of discrete behavior, you don't need the notion of time. Automatically, it's the opposite of time. So if you want to introduce it, do it on top of this. And the same applies to your second topic that was, what was your second?
Stochasticity.
Yes.
Stochastic.
On top of this. Do it on top of this. The match that we have in BPMN and in UML, etc., you can do it on top of this in a systematic way. Of course, we need much more involved formalism for special cases. And we should develop them. But we should develop them on a basis that is very simple, very natural, very mathematically well founded.
I totally agree that it's very natural and simple. That just to round it up, I think it was not really actually the thing that we were asking how to model it, but the biggest problem that we have is how to come to this understanding, which goes back to what you said, it's difficult to observe causality basically. So modeling it in this case, I would say it's easier than having dynamic compositions of systems, because in your case, for example, you just simply assume that you have nodes to connect the systems, etc. Doing these things that dynamically while the system lives is difficult.
I should talk more, but I have no time to about composition, for instance. Because you say, if you know all very, very many complicated composition operators, and now I come and say it's so simple. The point is, my suggestion is, if you want to make a complicated composition operator, do it, but do it on an adapter in between. The composition itself must remain simple, and if you want to express something complicated between A and B, make an adapter and do the complicated things into the adapter, then simply compose A with the adapter and the adapter with B. Okay?
And you discussed it in the past.
Nobody else? Okay, I thank you again and wish you good
Thank you.
Yeah, that's why I changed topic. Actually, in general, I changed the topic, but now it's on the phone. Wolfgang assured me invited me to just give me time, we can always change it.
Nice to meet you, Frank. Nice to meet you.
Also, I was considering briefly to present the same thing as it's over that I guess. That's really not related to what you can prep it.
Ja, aber was du dann sozusagen